Good evening. My name is Mark Barnico. I'm the executive director of the campus here, the University of Chicago campus. We have an online audience as well tonight, maybe over a couple hundred people. And so I'll be addressing the audience online as well as the audience that's here in person for the first time on our campus since January of 2020, which is pretty amazing. Yeah. So I wanted to make sure that I want a welcome to everybody that took the time to come here in person. And we hope this is just the beginning of many great in-person events that we have on this campus, we have planned for this campus. So tonight, our talk is called Designing Diversity for Sustained Innovation. And Professor James Evans will deliver that talk tonight. As always, we're sharing this program on Zoom live, as well as YouTube and Facebook live. So hopefully we'll pick up some more audience members to see our beautiful campus on those platforms as well. And I always like to remind everybody that we are available on our website. You can see just about everything that we do on our website at www.uchicago.hk. You can subscribe to our e-news there and stay up to date on the latest news and programming that we have on campus, whether it's virtual or in person or hybrid. All of that information can be found there, as well as following us on our Facebook and YouTube and Twitter and Instagram accounts, and LinkedIn. I forgot one. So today I'm really excited to host the in-person talk with Professor James Evans. He's the first UChicago faculty that's been back to Hong Kong to give a talk since 2020, as I mentioned. And Professor Evans is the Max Palevsky Professor of Sociology, the director of the Knowledge Lab, and the faculty director of the Master's Program in Computational Social Science at the University of Chicago. We came to know each other through some mutual contacts at the Santa Fe Institute, interestingly enough, which he's also an external professor too. And if you don't know about the Santa Fe Institute, I strongly encourage you to check that out. And maybe Professor Evans will tell us a little bit about that this evening. Professor Evans' research focuses on collective system of thinking and knowing, ranging from the distribution of attention and intuition, the origin of ideas and shared habits of reasoning, to processes of agreement and dispute, the accumulation of certainty and doubt, and the texture, novelty, ambiguity, topology of understanding. Can't wait to hear the talk tonight. He's especially interested in innovation. This is another area where he and I have very common interests. How new ideas and practices emerge, and the role that social and technical institutions like the internet, markets, collaborations play the collective cognition and discovery. So innovation is core to his work and my interests. Much of Professor Evans' work is focused on areas of modern science and technology, but he's also interested in other domains of knowledge. Again, very interesting layering here of news, law, religion, gossip, hunches, machine and historical models of thinking and knowing, as well as he is also the director of the Knowledge Lab at University of Chicago, which has collaborative granting and employment opportunities, as well as ongoing seminars. He also founded and now directs the Computational Social Science program at the University of Chicago and sponsors an associated computational social science workshop, which I hope he'll tell us more about tonight. Professor Evans' research has been published in Nature, Science, Proceedings of the National Academy of Science, American Journal of Sociology, and many other outlets. And his work has been featured in The Economist, which I'm sure many of you are familiar with here, Atlantic Monthly, Wired, NPR, BBC, CNN, the list goes on, Le Monde, and many other outlets. So without further ado, let me introduce you to our first UChicago faculty to come back to Hong Kong since January 2020. Thank you.
Thank you, Mark. Well, I'm delighted to be here, delighted to join with you tonight. Here, let me just share my screen and we'll go to town. Okay, does this go? Oh, there we go. Okay. So as Mark, and I'm gonna set a gentle chime for myself for 50 minutes so that that we can focus on your questions, and feel free to interrupt, with clarifying questions or contentious fundamental disagreements. I mean, I really, I look forward to your thoughts. I know what I'm going to talk about. So, as Mark mentioned, I run a little center called Knowledge Lab at the University of Chicago in sociology and computational social science. And I'm going to focus tonight on this idea of, understanding the nature and then designing diversity for various purposes, using some examples and alluding to others. The work that I do sits at the intersection of three broad areas. One is computational social science, which is just to say, how can we basically take not just technological tools, but technical imaginaries, right? Ideas from simulation and optimization and complexity. How can we bring those into thinking and rethinking what our project is in the social sciences? And that project in some ways can also be translated back into computation. How can we build societies and institutions that compute and produce more peace, prosperity, equality, outcomes that we desire? How can we think about these systems as systems that we can engineer and instrument and monitor and enhance? The other two things that you'll see me kind of talking a little bit about and intersect with this are the science of science and innovation, which is just how can we bring the entire imaginary of the sciences and computation, like all, the full range of epistemological tastes and approaches and tools to studying science itself. If you were to go to the National Institutes of Health, huge civilian science funding agency, the largest in the world, you might ask, well, what do you study? And they would say, I don't know. What's your portfolio? What are your more and less risky projects? They don't have a portfolio. They have a team of scientists from the last generation predicting what might be successful in the next generation. Projects on average are selected for their expected value of success. And so we end up having situations where we're not thinking about all the questions that social scientists, but also natural scientists think about. If we care about diversity, we want ecological models in the room. If we think about fields of interacting scientists and engineers, then we want solid state, and other physicists in the room who are modeling those spaces. If we, we want all of the ideas at the table. So this has been really a convening exercise. And then finally, putting those together, how do we think about creating artificial intelligence that augments human capacity rather than painting a bullseye on the back of humans and basically just trying to replicate and substitute for human labor and activity? How can we figure out what it is that humans individually and collectively do well, and then build artificial intelligence that does what they don't do well, right? That is, in fact, the least human, the most alien artificial intelligence, right? That will, in some ways, be the most informationally and task-wise relevant for human capacity. So these are things that we put together. And it's associated with a number of institutions that I'll just mention because Mark invited me to, that relate to some other programming that we'll, be happy to share with you. So, one is Knowledge Lab. We run seminars. Our computational social science program, we run weekly workshops with leaders in the field from around the world. We publish, a journal of social computing, actually joint with IEEE, which is kind of electronic and electrical engineer and computing publisher, and Tsinghua University Press. We also are really focused on running a number of conferences, which we'll advertise. I ran recently a conference on plurality, which is how to use blockchain and other kinds of technology to source the diversity of opinions in a complex decision-making process like democracies or community-based decision-making. And then we have, there's a new institute that I just began with some colleagues focused on trusted intelligence in society, which is to say trusted artificial intelligence. How do we not only understand and create and respond to AI, but also not all AI is explainable. Is anyone in the crowd here played with ChatGPT here? 1, 2, 3, 4. Okay. So ChatGPT, Switch C is another model that's related. These are big models. This is, Switch C is a 1.7 trillion parameter model. That's an engineering model. It's not a statistical model. These are not surveillable. They're not statistical objects. We don't know what the sigma algebra, that's the search space that you've learned to figure out that that's the right model. We don't know what that search space is. We can't describe it scientifically. And so rather than just opening up these models, because it's like opening up a complex car when you've never learned anything about engines, we also need to build other AIs to surveil and counterbalance the AIs that are running in the world. In the same way that we have checks and balances in government, we've got independent, or when we do have independent executive branches and legislatures and judicial branches, or if we have police in the community, and we're building AIs that are basically surveilling and testing and auditing and turning off other AIs in the context of valuable contexts. So anyway, those are some of the things that we're doing, and they all intersect in work that some of which I'll describe tonight. I would say the overall view that I'll be kind of proposing is, and the question that I'll be posing to you is, how does innovation and society as a system think, right? How does it think? And how can we think better together? How can we build institutions that do more of what we want, compute more of the answers and the solutions that we would find desirable? And I take a kind of a market view of knowledge in all this. And by market view, I just mean that knowledge ends up being effective and effectual insofar as it allows you to do better at the world, at the things that you want to do. And if you haven't done better at the things that you want to do, then you don't have effective knowledge in those domains. So we spend a lot of time measuring knowledge. And this knowledge is manifest in the context of texts, but also, articles, that are just self-describing, many other knowledge traces that I'll describe some of in the context of these remarks. And the overall intuition is that basically I'm trying to understand innovation, but using, this is the computational social science part, but using what I'll call the generative standard. And that generative standard is, if you didn't grow it, then you didn't explain it, right? So we're not just trying to create what we call necessary but not sufficient explanations that maybe explain with certainty a little part of the outcome. We're going to try to explain all of the outcome, or as much of the outcome as we can. And then if we can't, and then we're going to try to use that to, in many cases, automate innovation. If we can't automate innovation such that we do better, taking these social and cultural and technical processes into account, then I'm dubious that we understood them in the first place, right? So I spend a lot of time working with social scientists and natural scientists and finance people trying to predict better outcomes at high levels. We're working to identify investments that would be reasonable and engage in experimental catalysis of work. But I'm also working at low levels with groups like Andy Cooper. In this Nature article, he describes this robochemist. This is a robot chemist. He's got about 30 of them rolling around with LiDAR, laser-controlled, rollers in a big space inside this Liverpool lab that's supported by the Leverhulme Foundation, Unilever, and the idea is they're running, 1 million experiments a month. And so the idea is, well, can we take this philosophy of science and embed it as a program inside these robots and see if we can do better at identifying what they're trying to identify. In this case, better photocatalysts, better photovoltaic materials, better, and with other labs, pharmacological compounds, et cetera. So if you've got a lab that's big enough, that has a big enough budget for many experiments, which a big accelerator might have, or one of these high throughput experiment groups has, then you have enough for us to really test and tune and develop a process that works. So I'm going to begin with this idea from Francis Galton. Francis Galton was the cousin of Charles Darwin. And at the end of the 19th century, the beginning of the 20th century, he was a geneticist and a eugenicist. So every geneticist was a eugenicist. That was like public policy. It's like you're trying to understand and improve and enhance. He was and he had this intuition that we want really intelligent people making decisions in society. I don't care about the average intelligence. I want the tail of intelligence. We want the most intelligent people. And he engaged in an observational act that resulted in a 1907 paper in Nature magazine called Vox Populi, the voice of the people, that surprised him. That was the opposite of what he expected. He went to this West of England fat stock and poultry exhibition. So, people are rendering their cows, they're selling them, they're buying them, they're trading them, they're trading, meat. And Galton, what he did was he basically there was this procedure that he participated in, where 800 people wrote how many pounds they thought this dressed, so not alive, but dead cow was, or not cow, but steer. And the one that was closest would get the meat. So, which was a nice prize. Now, it wasn't like me or you, I'm guessing this, the weight of this steer. It was people who owned cows and steers, right? So each of them, and if they owned them, they knew how much it weighed, or if they were a fancier, or if they were a trader, they all had independent information, right? They might know the weight of theirs, and then they look at this one, and then they kind of, make a heuristic judgment about. So each person came in with diverse data and a diverse approach for assessing this. And then when you take the median of all the guesses, so this is not the most intelligent people, this is the people right smack dab in the middle. This is the average of all guesses, or the center of all guesses was 0.8% off. The average was less than 0.1% off. It was closer than any single individual in the crowd, right? So the crowd was smarter than any person in the crowd, and this was not his expectation, but it was a surprise. And I would say the broad field of what I'll call kind of collective intelligence really didn't give that full attention until the kind of computational era, post 2000. And since then, there've been a lot of efforts to try to build platforms and systems that will allow collectives to take advantage of this wisdom of crowds phenomena, where as a function of the diversity of underlying experiences with the world, and diversity of approaches to solving those aspects of the world, you do better on average for these complex problems. And so I'm going to be talking about different kinds of diversity. I'm going to be talking about cognitive diversity, people who think in different ways. I'll be talking about perceptual and experiential diversity, that people have different experiences. People see things or sense things in different ways. I'm going to spend less time, just because I don't have enough time, on identity-based diversity. When people talk about diversity, often they're talking about self-identifying groups, racial or gender, other groups to which people align. And that's, because I'm not focusing on it in this talk doesn't mean it's not important. It highly correlates with cognitive, perceptual, and experiential diversity. And what's interesting in recent work, some of it by some of my students, Rem Koning and others, has really focused on the power of identity-based diversity to impact not only the power of the solution, but the relevance of the solution. So, for example, he had a beautiful science paper about a year ago, a little over a year ago, which showed that it's harder for women to have access to the potential to be engaged in invention. But when they are in the context of health and reproductive health, they're much more likely to produce inventions that are relevant to women, that diffuse to women, right? So it's not just that we want to include people because we enhance the overall outcome, right? The general intelligence of the solution, which we do, and that's what I'll focus on in this talk. But if we don't, then the benefits actually don't cascade to those relevant groups in the same way. So I'm going to be talking about the wisdom of crowds, but from the perspective of the wisdom of scientific crowds, the wisdom of technological crowds, the wisdom of business crowds, the wisdom of online crowds. How do we think about taking some of these ideas, understanding them more deeply, seeing the degree to which they're relevant in the context of science and technology and online life and more. And there are three kind of chapters to what I'll be talking about, three ideas. One is that innovative crowds are characterized by something I'll call collective abduction and bridged difference. So they bridge difference between them, and I'll define collective abduction in just a minute. The second is more of a montage. We'll see how much time we have, but that connection and conformity between people is associated with reduced replication and impeded innovation. And this is, again, challenging and a little bit ironic because, of course, we think of these online networked crowds as sources of deep innovation. And while lots of people with distinct experiences can be sources of diverse, innovation or can catalyze diverse innovation, their networking can actually drive down the potential for them to innovate together, right? And then finally, I'll talk about AI that allows us to design diversity. In some cases, design pull together the right kinds of diversity for a particular task. In other cases, to design diversity that even sits beyond human experience, right? If we're able to kind of place human experience in some space, then can we discover and unleash or harvest diversities that exist outside that space of traditional experience? Can that basically inspire us to think about building institutions that really preserve and sustain diversity for the long run? So that's where I'm going. So how do innovative systems think? Well, philosophy has taught us cartoons of thinking, right? These aren't really how people think, but they're methods, structured methods of thinking that summarize in simplicity some of what people do. One is Aristotle's famous deduction, right? So he invented the syllogism, and the idea is you're logically extending new knowledge from existing and firm facts and axioms that you know, right? So that's one approach. Another polar approach, which was associated with the scientific revolution, was Francis Bacon's really promoted idea of induction, that you imaginatively generalize from observations. You see things in the world and then you imagine the kind of, and you're not ensured logical correctness, but it's imaginative act. And this was associated with experimentation that really resisted. And in fact, there's a wonderful kind of historical document right at the beginning of this thing called the Royal Society, which was built on Francis Bacon's ideas, which said that you couldn't basically be inspired or develop experiments as a function of systems. And by systems, they meant theories. So they were really trying to get rid of the idea of classical knowledge and start over again. But the problem is, again, these are poles, right? So very rarely do we begin looking at the world without any preconceptions. Very rarely do we go or learn radically new things from things that we already knew before. And so Charles Sanders Peirce, the great American 19th century philosopher, described a different form of reasoning called abduction. He argued that almost every recent advance in science and technology and business came about from the creative production of new ideas and hypotheses based on surprising evidence or theory-defying evidence. So this is like the car crash between induction and deduction, right? You set out an experiment, right, with the expectation that you'll find something, and then the world happens and you do not find that. Or you set out on an expedition to observe something, Jane Goodall, wandering through the forest looking at chimpanzees, and she sees something that no one has ever thought to see before, which is that these apes are using tools, right, in ways that people thought it was inconceivable previously. And she was shouted down in Oxford when she presented these early results. So this surprise effectively is the thing that drives attention and that motivates additional hypotheses in a range of contexts. Now, to measure this, this is a nice idea, but how do we actually measure this at scale? Surprise is difficult to measure. And the reason it's difficult to measure is because it requires a sufficient model. What does that mean? It just means, in a nerdy way, that we have to predict almost everything to be able to anticipate with our model the things that would in fact be surprising to people. Like if we can't predict almost everything that people can predict, then it's very unlikely that things that are surprising to our model will also be surprising to the people, right? We have to build a kind of a digital double of this system, right? To think the way the system's thinking. So when the double is surprised, people are surprised, and we can use that as a tool to learn, in this case, about how science thinks. So we're going to suggest that novelty in terms of outcomes, so things that are potential innovations, are improbable, right? So novelty is inversely proportional to the probability of some invention or some discovery or some new business or new institution or some phrase, right, conditional on the prior things that have been said, the prior structure of invention, and the prior process by which old things become new things. So there are many things that are surprising but stupid, like the dumb phone, not a great business model. I mean, maybe it is, maybe for someone who needs to tone while they're communicating. So there are lots of things that are surprising for different kinds of reasons. And so we're going to explore that full range of novelties as they're generated by science and business and technology. In this particular case, I'm going to try to build a model of new inventions, new discoveries, new technologies. My representation of these is going to be pretty impoverished. It's going to be pretty weak. It's going to be like a bag of keywords. But I'm going to try to predict every bag of keywords. I'm going to try to predict every paper that's published next year, every patent that's published next year, and in the next 5 years, each year, right? So this is the game. This is the challenge. And there's the two ways I'm going to represent these are, one, as a bag of contents, a bag of keywords that represent concepts, phenomena, tools, right? So, a recipe, if you will, right, for the discovery that comes out. In another, I'm going to represent these as bags of contexts, right? Journals, conferences, conversations, right, through which a new invention or discovery was arrived at, right? And so contents that are unlikely to have been successfully, so surprising combinations of contents are unlikely to have been combined before successfully. That's why they weren't in the literature. Contexts that haven't been combined before are unlikely to have been imagined before. There's nobody who's sitting across these conversations. So I'm going to look at this in the context of a bunch of data, about 20 million biological science articles, about 1 million physics and physical sciences articles, and a couple of million US patents. I'm going to analyze each of these separately to see if we see the same set of patterns. These findings will be published next week in Nature Communications. So the game that I'm going to play is I'm going to create a it's an embedding And what I mean by embedding is just a space. I'm going to create a space of all these keywords or all these journals, right? And it's a high dimensional space. This is just a two-dimensional representation of the space, but we figure out what's the best set of dimensions that allow us to predict the next set of papers. In this case, it's like 36 dimensions. It's a lot of dimensions. And we basically put these keywords all over the space randomly, and then we draw down a bunch of sets. A bunch of sets we call a hypergraph. A graph is like a bunch of things that are connected together. A hypergraph is a bunch of sets that are overlapping. So that's what we're trying to predict, is all these sets. And then what we do is we wrinkle this space of keywords or journals. We wrinkle it until we maximize the likelihood that we predict the actual papers that show up in a year. And that sounds like a really arbitrary process, but it turns out that when you do that, enough times you optimize this process, then the dimensions that pop out are actually real dimensions. I mean, they look like real things in the world. And so that's the game we're gonna play. We're gonna try to maximize the likelihood of the space to predict this graph. And then we're gonna just let this graph evolve, and then we're gonna pull down, another hypergraph next year, and that's our prediction for next year. And it does pretty well. So this is the evolution of that graph, that space, and the pulling down of that graph over time. And these are the dimensions that kind of pop out. So in the biomedical context, you've got substance abuse popping out as a single dimension in the space. You've got skin diseases all popping out in the space. You've got jaw, dental, and oral medicine popping out in this. So we didn't do anything. We didn't tell it. We didn't, suggest that these are just the dimensions that naturally emerged as a function of identifying these optimal predictions. And this is what a paper looks like. Again, it's a wimpy looking paper, but it's, that dashed line is a new paper in 1982. We're combining aminoacetonitrile with acetamides to study drug-induced liver injuries in rats, right? So that's the recipe for that paper. There's never been a paper before that paper that explored those things with those technologies and those methods. So that's the recipe, and that's what we're trying to predict. We're trying to predict all of those, in any particular point in time. And I would say the challenge, this is the nerdy part. There's a whole techniques to this. We don't have to go deeply into it, but, I'm in it, so this is what I love, I'll stop. But, here it's like the thing that's complicated about this is that everything is close to everything else in this space, right? Everything is two steps from everything else, like 6 degrees of separation, the Kevin Bacon game, like this distance across the world. Well, in these spaces where people are talking with one another and working together, everything's close, which means it's one big mess. And so we need to really build models that allow us to see through this complex morass of representations. Let me just look at my time here. Okay, so this is a really unusual paper, and the green one. See, the green one is pulling on these keywords that are way far apart. And way far apart means no one has ever combined these before. So we didn't wrinkle the space to bring them close together. We wrinkled the space to pull them far apart. And so that's a really unusual paper. So we can invert this model such that the papers that come out that are the least probable under this most probable model are surprising to the model, and they are surprising to the people in this space. And so this model is kind of a model of how the system thinks effectively. And so this particular paper, it's combining a whole bunch of things that we knew were in animals, and they discovered them with a new technique in plants. So it was kind of like, wow, all these things we thought about were, essential and deeply connected to motility, to movement, are now just part of the plant universe. And it forced a whole host of rethinkings in that space. It turns out if you look at the papers that are surprising from the perspective of their contents, they're like an unusual finding. if they're surprising from the perspective of their context, it's a controversial finding. It's an unusual hypothesis, right? So as we kind of anticipated, this is modeling the way in which people are thinking about this. So these are people, these are experts who read papers, and then their favorite papers, they annotate them with codes that represent how surprising or novel or interesting or whatever they are. It turns out as they get more surprising in content, they're more likely to get awards. We mapped every award that's given in biology, medicine, chemistry, physiology. We did the same for physics. It turns out it's kind of funny. If you look at content novelty, it's way more predictive of attention, of citation attention. But it's much less predictive of awards. And the reason is because awards are given by contexts. It's like the physics committee, at in the Nobel Prize Committee. They're not giving awards to things that violate the boundaries of physics systematically. They're giving things to things that are inside. But these things that are violating contexts are not. These are transdisciplinary inventions and discoveries. And when you put them together, when you add them together, you can predict like about 50 to 60% of the likelihood of being in the top 10% of citations. And again, we don't know anything about the people. We don't know they went to Harvard or, and we have no idea who discovered what. All we know is that if this is true, this thing that's published, it's surprising to this system. And those things that are surprising to the system are massively attracting attention in the system. Science and technology are dramatically attention-seeking, surprise-seeking systems. They're driven by these abductions. And we asked, well, who makes these? Oh, and the same is true for physics and invention. Anyway, so science and technology are a little different from each other because in science, you have to get people in your field to approve your paper for publication. And so what it turns out is that you reference things that are familiar to your audience about 500% more than things that are unfamiliar to your audience, because you're not an idiot. You know that they're the people who are actually going to be deciding whether you can go inside or not. Patents does exactly the opposite. You're more likely to reference things far away because you want the freedom of action to basically build your invention without being encumbered by something else. So the incentives drive how it is that people talk about what they discover, and it actually describes the attention across the system. So patents as a system, people who are pursuing patents are much more likely to spread across the whole knowledge scape. They're more likely to know less about more, whereas in publications, they're much more concentrated. They're much more likely to know more about less, right? About things that they know that other people care about in that space, which suggests something about how, science, as open as it is, it's also a very cliquish space. Now we ask the question, okay, so who comes up with these things, right? Who comes up with the surprising things? Are they surprising people? People have had unusual backgrounds. They went to this school, they shifted to that field, they went to this place. Are they unusual teams that bring people together with really diverse expertise? Or are they surprising events where people come from one field, one space, and they travel across the space of knowledge and solve problems for a community that's never seen people like them before? No one from their community has ever seen problems like this before. And it turns out that systematically across every area that we look at, that expeditions are the most likely to predict this outsized novelty. I mean, teams and careers kind of require a social contract. It kind of requires that everyone expects something's going to work. These expeditions are bets, and these bets sometimes work. And when they work dramatically. They rewire the whole system of collective knowledge in this space. So this radical insight really comes out of conversations between insiders within the fields, people who own the journals effectively, and outsiders or aliens to those fields. And it turns out, the same is true for business. So it's a little more complicated in business because if you are starting a venture-funded startup, you have to succeed really fast. How much time do you have, Mark, when you have, a first round of venture funding before you have to show some kind of product or you're dead? Okay, less than a year, right? So when we looked in these spaces, first we tried to figure out, okay, what are they combining? And it turns out that the ventures that end up being much more likely to have a successful outcome, which is to say, an initial public offering that's successful, a high-priced acquisition. These are firms that they combine unusual things, but there's special kinds of combinations. Those combinations are technologies that are already well applied to certain problems or areas. And they take these well-applied technologies and they combine those things that are already working and already functioning into a system that either works or it doesn't work within a year, right? So there's novelty in the space, but it's really applied novelty. It's not the novelty of exploring new properties or applying technologies to new problems, which is usually what comes out of universities, which usually fails. It's taking existing components. Think about Uber. It's taking existing working components and putting them together in the context of a value-producing system. So again, a similar kind of logic, different kinds of constraints that shape how it is that, say, entrepreneurship thinks than how science and technology think as systems. That being said, a key character of modern science and technology is increasingly searching farther and farther from your problem space to solve your conundrums, right? So increasingly, other sciences act like reservoirs of difference that you dip into systematically to solve your problems, right? So if everyone was speaking to everyone else, everyone was converging to the same problems, then you wouldn't have really modern science as we know it emerging really through the 60s and then kind of flattening thereafter, which is when sciences really became peak at reaching out. These are the things that you cite or reference. You're drawing on things that are really much further away from you than before. You're solving your problems with other people's alien logics, technologies, patterns, etc. So, okay, that was kind of part one, this collective abduction that we end up being driven by surprise in these systems. And the second piece is another aspect that kind of underlies the importance of diversity and designing, preserving, conserving diversity in these systems to create sustainable advance. So across innovators, across teams, across fields, systematically, we see that dense social connections distort collective certainty, and they slow novel discovery and invention. So when everyone's talking to everybody else in these systems, or everyone's connected within the same team or the same conversation, everyone's publishing in the same journal, then the diversity collapses in these systems in ways that I'll show in just a minute. So we have a number of papers that have come out in the last few years that show that large, tall, and sparse teams dampen disruption, whereas small, flattened, smooth teams amplify it systematically across this space. So again, to say this, of course, I could be talking about, like my experience with one or two teams, but to really persuade people who are not predisposed to agree with me, I have to build some kind of measurement, some robust measurement that I can measure, in this case, across 100 million teams that have been doing invention and discovery over the past, hundreds of years. I mean, and so what we did was we developed, or we borrowed, really, actually, this was really satisfying. This measure was developed by a former undergraduate student of mine who's now at the University of Minnesota. So he published a paper And in fact, he just published another paper in Nature 2 weeks ago that uses this to show how disruption is declining. But we use this measure, and what it shows is that when you talk about an invention or an idea or a movie or any cultural object, right? You can talk about it in two ways. You can talk about it as the next step in a sequence, right? So like I'm going to talk about abduction as a function of induction and deduction, like it's the next step, or I can just talk about it as the thing, like the starting point. It's not another step in the development of something. It eclipses its own history. Like when people talk about me, they don't talk about the things that I even say that I've built on. They only talk about me. I'm so different, or my invention or discovery is so different. So we build this, it's a very simple measure, but it's extremely powerful, right? For example, so it's the degree to which you eclipse the things on which you build to the people who tell stories about your things afterwards, right? And so you can, any context can generate a robust association of this measure. And if you basically run this through every paper that was written in the last 100 years, then, for example, these are the words that just happen to correlate most with being the most developmental or the most disruptive. So again, we didn't use words in creating this measure. We just used the simple structural measure of the degree to which you eclipse the things that you build on. But the things that are the most disruptive happened to be correlated with the words change, introduce, and advance, while the things that happen to be the most developmental from this totally structural measure are things that endorse, confirm, and demonstrate. Theory, model, and hypothesis versus tool, device, and technique. Across, within, and along versus how, what, and why. These are the prepositions that just happen to be the most correlated with one or the other. So these are effectively self-describing, right? So disruptive things, even when they were published, even though this measure is about what happens long afterwards, end up looking very different. And basically, we're trying to capture this association of things that are more disruptive, that change the landscape, that refocus people's thinking. And we find that big teams are exponentially, that's much, much less likely to produce papers that are disruptive, right? That eclipse the things on which they build than small teams, right? They're much, much less. It doesn't matter how you cut this, what team size is, where you slice it in the distribution. It's always the same across all contexts. We looked at it across software development. We looked at it across patents. We looked at it across papers, company developments. And then another thing is the structure of the team, right? It's not just large teams that depress innovation, but hierarchical teams depress innovation. Now, how do you measure that at scale? Right? Because we wanted to measure this again at this scale of tens of millions or hundreds of millions of teams. Well, there's been this movement towards transparency and fairness in publications where you actually have to say who did what, right? And if you cluster who did what across all the things that anyone has said that they've done, this is what you get. You get 3 clusters of things. One is leading, writing, supervising, conceiving, coordinating, designing, and interpreting. Like this is the leading category. These are people who are designing or describing themselves, crediting themselves as having done those things, versus conducting, collecting, analyzing, purifying, carrying this thing, and versus I enjoy this one here, commenting, editing, providing. This is like the weakest form of indirect contribution to this thing. So we basically tried to build just a simple capture of the hierarchy of these teams by taking the ratio of the people on the teams that are leaders, right? So everyone can be a leader. Everyone can put their brain trust into the project, or you can have one leader and everyone else is a peon, everyone's a laborer, just carrying, purifying, jiggling, whatever it is that they're doing a Southwestern blot. And we assessed this over all the papers that we could assess it with, over 100,000 plus papers. And then we were able to extrapolate that to the whole system, because it turns out that that likelihood of someone's contribution as a leader was almost perfectly predicted by whether they contributed references, topics, whether they were leaders or corresponders, their age, the degree to which they had topic diversity across their space. So we could extrapolate this to the universe of all papers. And what we find, again, systematically, is that more, and this is controlling for team size, right? That basically more hierarchical papers are much less likely to produce novel combinations of outputs. They're much less likely to disrupt. They're much less likely to produce equitable productivity for people across the systems, and they're much less likely to influence the far future, right? It's like a production company, right? If you're a movie production company and you're tasked with, like picking the movie to produce, are you going to select the next independent script, like Slumdog Millionaire, or are you going to pick Transformers 9, right? You're going to pick Transformers 9 because it's going to get the receipts of Transformers 8 minus epsilon, right? It's going to get, like, all the people who went to see Transformers 8 or get maybe more are going to go to Transformers 9. So what big teams do is they just look at yesterday's hits and they increment on them, because they know that the market is the same. The people who love Transformers 8 are going to love, the people who love those papers are going to love our papers. They don't move the needle. They don't transform the space. They're like momentum investors. Looks like these are, and it turns out the same is true for fields as a whole. So we had this paper where we looked at what happens when fields grow, because all these fields are growing, like biology is growing, neuroscience is growing. And what happens is, and philosophy is growing. As these fields grow, it becomes also exponentially, which again just means much, much less likely for new ideas to enter the canon of highly cited works, right? It's almost like there's a social contract of the conversation. If we're all part of the same conversation, then the diversity of our ideas collapses, right, into a single point, into a single conversation, into a single channel in this space across fields. So, and this is, there's ways to think about this formally, which I don't think I'll mention, but we've studied this in other cases. This is in 21st century physics. We've looked at collaborations when departments start collaborating more with one another, then the number of ideas that they generate collectively goes down dramatically. And it's much more likely for the collaboration to drive the reduction in ideas than the reduction in ideas to drive collaboration, right? So, and we see this in other places, like cultural objects on the interweb. Something becomes popular here and it becomes popular everywhere. Language extinction with social contact, like the little islands of the Philippines where every island speaks their own language. They become to contact and trade and other things end up driving down, specific culturally evolved codes, or biological extinction with ecological contact, right? So we see this diversity in other biological and physical contexts. We see it just as prominently in the scientific context. So another idea in this space relates to what people have often called in the last few years, I'm going to have to speed up a little bit here, the reproducibility crisis. So what this is just this idea that's emerged, I would say, over the last 18, 19 years, that basically most findings are not reproducible from scientific journals. That's not surprising to many of us who didn't think that they were reproducible to begin with, but it just turns out, that most findings, if we experiment independently, they just don't work in the same way. And it turns out that this has been devastating for certain areas, for example, of social psychology, but also genetics. Medicine is the place in which this emerged initially, genetic findings, pharmacology, et cetera. So, and it turns out, what generates more or less reproducible findings was the question that we were asking ourselves. And what we find is centralized communities, connected communities produce much less replicable findings that are much less likely to work outside the context of those groups. The way in which we tested this, we've tested this in a ton of different places, but here's one example. We take all of the claims from, let's say, the literature about, in this case, drugs that influence disease-related genes. And then we connect with, or run, in some cases, a high-throughput experiment. This is an experiment. It's a wet lab experiment. It's been driven by robots. And in this case, it reproduces each experiment 200 times. Okay, this says I got to finish up really soon if I want your ideas. So I'm gonna try to do that. And what we find systematically when we look at this is so this allows us to basically look at, okay, we can look at the connection between the researchers that produce those findings, and then we can look at the likelihood that they reproduce or don't reproduce under 200 different conditions. And what we find systematically is that science kind of works like when more people publish something, it's more likely to turn out to be true. But when there's more centralization in those communities, when the same people are on all the papers, like a center director or a postdoc who's traveling across them, or if they have the same authors, they have used the same methods, they rely on the same prior knowledge, they reference the same papers, they have the same expectations, then the findings are much, much less likely to replicate, right? And the reason is because maybe there's 100 papers that makes a claim, but, there's like, if there's 100 papers, it could be like 1.2 independent experiments because they're all talking with one another. They're all sharing the same cell lines, right? They're performing it in precisely the same way. If you vary any of those things, then the findings break across this space. And we look at this in other contexts. You can see that if ideas don't diffuse, right? So these are two papers, a paper by Piero and Versa, who was widely heralded for his paper on stem cell cardiac regeneration, versus Tasuku Honji for his cancer immunotherapy paper. And what we find is that Piero and Versa, his work did not diffuse. Lots of people cited it, but all those people were his friends. All those people were co-authors of his. He had lots of co-authors. All those people were studying almost exactly the same systems and cases. So even though a ton of sites occurred, it's like this bubble, like a market bubble. It's like everyone's talking to one another. Everyone's reinforcing the fact that this finding is there, but it's just not diffusing. And those diffusion bubbles, just the size of that bubble, that lack of diffusion predicts the ability or the likelihood that knowledge is going to collapse. And not only did it collapse, but, he was fired from Harvard. Almost all of his papers were retracted or cast into serious doubt. Tasuku Honji, his ideas did not, there was no bubble, but they diffused rapidly. And that rapid diffusion across different kinds of people, different kinds of fields, different kinds of other contexts were associated with its dramatic uptake and success. And so you could predict years farther in advance the likelihood that something is really going to be robust, just as a function of the diversity and disconnection between the people that are analyzing or studying it. And you can turn this around and use this as an instrument to basically predict the likelihood that these things will replicate in the future. And I should say too, this is also, we look at this in the context of social media. So we've looked at this in the context of Wikipedia contributions. If you have more political diversity underlying the editing of any particular page, then people who are completely unaware of how those pages were created are much more likely to assess, especially if the page is about a political topic, that underlying political diversity generates much more high quality pages, right? There's more arguments there's more perspective that gets incorporated into this singular page. We look at this across, millions of contributors and hundreds of thousands of pages. So this is true in social media. It's true in software development and design. It's true in the context of science. Okay, can we turn this around and design diversity to increase collective imagination? Can we use this principle to kind of automate science and see if that does something interesting, right? If it does what it is that we want. And so here's a little case. Now, typically, when we think about AI, we think about Alan Turing's imitation game. We're going to try to create an AI that thinks like, indistinguishably from the outcome of a human intellect, right? And the classic game is, there's a hole in the wall, and you get, an answer through that hole, and you have to decide, is the person on the other side a human? Are they a machine? And there are other ways in which machine learning made that even more extreme. Rather than just mapping the humanity effectively of the outcome, we're going to try to learn from the moves that people are making, right, directly. But the real question, and this is the way, when we say AI, this is just a Google search, an image search. I mean, these are brains, like people are thinking, this is a humanoid brain, in the same way that but the problem is, I'd argue that, we've got almost 8 billion humans, and it's not obvious that this is the most ethical or the most efficient investment in computational intelligence, is to basically create things that identify human capacities and replace them. And so I'm going to explore the possibility of doing something different, augmenting human intellect. There were people who thought about this. This is Doug Engelbart's mother of all demos in the 1960s, where he showcased the mouse and file systems hyperlinks for the first time in a single demo. So the way in which they thought about augmenting humans was really, how can we basically create interfaces that reduce the friction of information? You can just use your mind to control all information. The problem is there's diminishing margin of returns to that, because it's just you thinking. So how can we think differently? How can we create an alien intelligence that thinks the least like us, and, that's diverse from us? And will that allow us to think collectively better than we could alone, right? So, here's my one little case, and then I will wrap up and take a half hour of questions. So this is a paper, not a paper from mine. This is a paper from some material scientists at Berkeley Labs. And what they did was they took all the scientific literature and they put it into a big AI model, kind of like ChatGPT, but a little more primitive. And they predicted materials that would have really desirable properties, like photovoltaic capacity, the ability to turn, light into energy, or to store that energy, or thermoelectric capacity. You create basically an electric current from differences in the temperature of some material. And then they found that if they embedded all those things, that literature in some big AI model, that model kind of captured a lot of the knowledge that was in the literature, and then it made inferences that were pretty good, like about 40% of them worked, which is to say that they would be discovered in the next 20 years by humans. In this context, we thought, well, we're social scientists. What if we wanted to make these things both more human and less human? How do we really build a digital double of the scientific system that's producing these discoveries? And then how can we augment that system to think differently, think better? So we thought, well, what inferences are the most likely? Well, they're inferences that are available to particular people. If a person is aware of a property and aware of a material, then they're likely to consider whether that material has that property. And if there's no person that's available to think about those things, because there's no one who studies both that property and that material, then it's very unlikely for it to be discovered, because there's no one to discover it. So how to, again, measurement, right? So how do we measure this at scale? So we build, again, little hypergraph, so again, in this case, it's a bag that bag contains properties, and it contains materials, and it contains people, right? And so we have this evolving hypergraph. Every new paper is a bag of these things that overlaps with the last ones. And instead of just embedding the literature like ChatGPT does, we're going to do something a little different. We're going to run a random walk. We're going to start at the property. We're going to jump to a paper with the property. We're going to jump to a material inside the paper, jump to another paper with that material, jump to an author in that paper, jump to another paper by that author. So what that is doing is basically creating a set of inferences from the front to the back of those walks. Like you start with the property, you end with the material. The density of those walks is going to be precisely proportional. We ran about 1 billion random walks over this space, over this literature. And the density of those walks is going to be precisely proportional to the cognitive availability of the idea, of the idea that that property has that, is encapsulated in that material. If there's no walk that connects the property and the material, there's no person who has been educated in these two things. This is a valley of death. There's nobody there. So we now embed these walks instead of the literature. We use a kind of a ChatGPT style model, and we do 100 to 400% better. So we're predicting almost everything we predict ends up getting discovered. It's like, 95% of the things that we predict will be discovered are discovered. Because we do that because we're just predicting at the top of these ridges of people. These ridges are these are density plots of here are the people who were thinking about this stuff. So this is it's interesting, but it's kind of lame. It's like a scoop machine. We're telling the future, but it's like the next year future. If we published all these discoveries, we'd just put a bunch of people out of jobs. Like we wouldn't generate any new knowledge. We'd just be killing the goose that lays the golden eggs. We'd be killing the people on whose data we've generated these ideas. So how do we do better? By avoiding people. And now I really will finish. I should say also, we did it for a ton of different things. We did it for 450 diseases, looking at drugs relevant to them, repurposing drugs. We looked into it for a bunch of different energy things. We looked at COVID vaccines. We're also, what's interesting is we're kind of able also to predict who discovers what, right? Because the who is the person who sits between the material and the discovery. And it turns out we're similarly able to predict this for who's going to make that movie, because that person sits between these literatures as a function of their historical experience. And so we're able to kind of objectively measure subjectivity, objectively measure where it is that people are thinking in these spaces. Okay, so how can we avoid people? How can we make these not the most human, but the most alien AIs? Okay. So how can we take walks that will never be taken by people? They're scientifically plausible. These are things that are close to each other in scientific space, but there are no people that bridge them. So we're going to basically arbitrage, these high dimensional holes that sit all across this space. And it turns out, okay, when we do this, when we discover stuff, when our little thing proposes, when our AI proposes things, if they're discovered in the literature, they're discovered years further into the future, because science has to reorganize before they would be discovered. They're obviously more distinct from the space of hypotheses that scientists are uncovering, and they're better. On average, they're better. Why are they better? Well, because even though there is the wisdom of crowds, we are pack animals. Scientists are pack animals. We are, no one wants to die in the forest alone. No one wants to ask an unlikely question that was false. No one's going to get cited for that. No one's going to get promoted no one's going to survive, and so what we find is that systematically, when you avoid people, you just do better. These properties or these materials have more photovoltaic capacity, right, on average. And this is even with first principle simulations. You can run experiments. On average, they do even better. This is a conservative estimate. Again, we're building diversity that didn't exist in the system by looking at the biases of the whole system. All this to suggest that, technology and enterprise and also culture and the arts. I have other examples that I could go through, advance through or could advance through AI provocation. So you can build ensembles of diverse intelligences that incorporate people with different experiences and bots that have experiences that no people have, right? That take these principles to their extremes, to absurdity. But in some cases, in many cases, they actually allow us to engage and advance. All this allows us to think about and reformulate in our minds how to build AI that makes a big difference. If we want an AI that is going to change things, we need an AI that augments intelligence by programming past limits of human reason and training diverse ensembles of human and alien intelligences to solve our most challenging problems. And that we need to design diversity in order to catalyze advance, and we need to preserve and conserve diversity to keep those reservoirs of difference available for us to draw upon when needed. And I'm going to skip over this footnote here. But the idea here is that, in the evolving sustainable innovation, often we talk about promoting bridging and brokering. All these things are important, but it's much more important to protect independence, to protect difference that's available for bridging when needed, right? Which preserves the diversity and the diameter, of the ideas within a system. So with that, I'll close. These are some of the folks in the lab who've been so helpful over the years in these various projects. So I'd love to take your questions.
What an incredible talk for our first talk back since 2020. Thank you so much.
Sure.
That was excellent. Who's going to start us off with a question?
To look at the innovation, to look at different ways to discover knowledge and all these things. Now we can look at say 20 years ago, 30 years ago, and compare to now. I mean, we feel that nowadays, if you are academic, you never have enough time to read all the papers. There seems to be more. Of course, it may be just more people, or it may be each person is producing more. But somebody told me that on average, each person is producing about the same. So the question I have for you is actually, did you look into do this kind of comparison historically to maybe know whether we are doing better or we are? I mean, I think nowadays all the universities are pushing people harder, my impression. But or maybe there's a difference between East and West. I mean, I think
there's no difference.
No difference, right? But
no.
So my question is that I mean, in the old days when I was doing my PhD, I mean, I didn't have to write, so many papers to get a PhD. I mean, many people have this experience before, but nowadays its criteria is very high. And so my question is really I mean, with all the methods you have, and did you do this kind of comparison? So maybe we can learn something about whether we are moving in the right direction or
Sure.
Yeah,
I can answer this. So I can't answer the why of all these things, but the patterns are totally clear. In fact, using some of those same set of measures and technologies, my same undergrad at UChicago published this wonderful paper in Nature 3 weeks ago that got a lot of press that basically showed this real collapse over time in papers that are disrupting the scientific space. And they're really, it's not just this measure, which you may think of as brittle. It's also that, just the combinations of ideas are much, the churn of ideas is on average dramatically decreasing over time. Now, the number of papers that are disruptive is the same over historical time. There are many, many more scientists engaged in science, and their activities are on average much more conservative, right? So science as a whole is kind of like moving at effectively the same rate with many, many more people and much more investment. Now, that doesn't answer the question of why. There's two big canonical answers. One is that nature is just getting harder. We've just picked the low-hanging fruits. We have to climb up harder, higher in the tree, and it's just harder. It could be nature, but it also could be that we have created an institutional system that incentivizes incremental work, that reinforces and rewards things that are close in this space. And it turns out that the evidence points to at least a substantial portion of this is accountable by these institutions. So, for example, if you look at the first grant that somebody gets, older and older and older, the likelihood that you get the Nobel Prize older and older and older, in like 10 years, everyone will be dead. Whoever who's, I mean, if it follows the trends, of course, they can't, by definition, they can't be dead. So, but the first invention is not older and older. It's the same, constant over time. So there are incentives and institutions, which it's not just that we have, all the low-hanging fruit has been picked. It's that, all the low-hanging fruit on the trees that we've decided are the only trees that we're going to pluck from. There are other combinations, there are other trees that no one's harvesting from. But in technology, where you're not incentivized with the same institutions, it's different. So
just a quick follow-up. So if it's true that we are investing more and more, but discovering it about the same rate, do you, through your study, do you have? Obviously there may be many ways to improve. How the rate of, if we're investing
there are
more,
many ways to
but,
improve.
what are the top 1 or 2 things you think we might do differently in today's university that will give us better returns, instead of
Yeah, I think one of the biggest things is we need a public education about failure. Failure is correlated with success, and we have a decreasing appetite for failure in these systems. So, for example, when you apply for an NIH grant, you're evaluated on its expected value, right? The average likelihood that it's going to succeed. So, people do studies upon studies just to apply for the grant to demonstrate that it's necessarily going to succeed. If grants funded in that way are doomed to succeed. They have to succeed, but they'll just succeed in like the most minuscule, marginally irrelevant way. So but the challenge is, things that fail dramatically end up driving public attention, and people point their fingers at the politicians who funded that failed project, that ridiculous research project. And so it requires a public education about the correlation of failure with dramatic success. We need to, and I would say researchers individually, if all of your research projects are succeeding, you are not a genius, right? You are scared, So I think this is,
Thank you very much and for this and very inspiring talk about this one. I'm really interested in your prediction about the journal publication, the influence, and all those things there. As a journal editor by myself, and we sometimes got like authors and fire back that you guys are nearsighted. You did not see the value of my research. Which is true, in some cases, it goes somewhere else and gets this published there.
Mhm.
My question for you is, since you use a very interesting data, since like 1835 to always young today, can we predict someone's and the research which have that latent influence? You moments ago show Alan Turing, and as soon as you publish your article, even by Turing, may not immediately recognized by the world. 10 years later, 5 years later, we think, oh, you are a good researcher, you are, wonderful scholars there. Can your, prediction can really say, certain type of like a finding discovery could be more innovative, disruptive, down the road, may not necessarily mean in 1 year or 2.
Yeah. So the measures that we're looking at, and all the things that we've shown that I was talking about in terms of like teams and the unusual combinations, all these things are much more likely to be successful in the long term, not in the short term. So things that basically build incrementally on the past, they do succeed in the same way that Transformers 9 succeeds because Transformers 8 succeeded, because you'll have the same audience, right? But if you publish a paper with no audience, right, then yes, it is one of the things that the future selects from. If it succeeds, it will dramatically succeed, but it may never be discovered, or it may only be discovered. I love, I don't know if anyone's read Aronowitz's wonderful recent award-winning biography of Leonardo da Vinci. It's all from the notebooks. It's so beautiful. And it shows that, I mean, there are a number of insights that he himself had to rediscover because he hadn't written them down in some other way, but that weren't discovered again for 500 years, right, about human health. I mean, 500 years. So, you know, those notebooks were not influential in that sense. They just suggested that this was like a really, really smart person, but they didn't influence the future. And I think this is one of the challenges with the scientific system, is it has a very short memory. And so often things have to be rediscovered you know, for the system to be aware that it was a possibility from the past. So it's true that science increasingly is like a blockbuster film system. Like if you don't succeed on the first weekend, you know, you're getting pulled from the theaters, and no one's going to remember that you're there. So this is a real challenge. So we can predict the likelihood, that we can predict the variance of future influence. And we can predict the degree to which those papers surprise the system. And so the question is, you know, like, I'll just give you one concrete example. I threw up a picture I didn't even mention. So, you know, this discovery, for example, that ulcers were generated from a particular bacterium rather than from the theory of humors, right? But this is in the 1980s. This is a physician in Australia from a very minor medical facility who had this hypothesis, and nobody wanted him to test it. No one would allow him to test like off-the-shelf antibiotics against ulcers. And so he infected himself with ulcers by drinking basically, you know, Helicobacter pylobacter infected broth, and then cured himself with a round of antibiotics. Even then, it took, you know, like 25 years basically for it to become routine for gastroenterologists to prescribe, you know, off-the-shelf antibiotics, right? Because there was a $30 billion industry of, you know, antacids based on this theory of humor, you know. So I think there are lots of reasons why things don't take off or take a long time to take off. And we can predict some things, but we can't predict others. But some of these things we can't predict. We could predict it was going to take a long time for that discovery to make it into medical science, even though it's, you know, completely obvious once demonstrated, right? So.
Thank you, James, for such a wonderful talk. I think the follow-up questions is about the definition of innovation. Through the talk, you kind of define innovation have several indicators. Citation is one of them. But think about Van Gogh. When he was alive, his painting is not being well recognized. So if we put it into the citation metaphor, no one cite him at all. So I think if you change,
Well, there's a lot of people that cite him now.
Exactly. It's
Yeah.
after how many years? So there's a time factor there.
Yes.
So I'm just wondering if we collectively redefined what is innovation. Do you see a different pattern? For example, if you use the same set of methodology to analyze the grant records, to analyze the publication in social science instead of science, you might see a different pattern?
So, I mean, I think this is, I'll just, you know, one definition I was not clear about is I'm talking about two things which are related, but not the same thing. One is novelty, which is something that's new to the world or new to you or new to a system, and an innovation, which is a novelty that takes off and becomes popular. becomes influential, that becomes prevalent, right? So these are the two things that I'm thinking about separately, right? I'm measuring novelty and the likelihood that that novelty becomes an innovation. You know, in science and technological and other surprise-seeking systems like haute couture, you know, and other places, we see the novelty ends up being correlated with the likelihood that something ends up getting picked up and influencing the future. This question of time, like how long does it take something to influence the future, is precisely related to how novel that thing is, right? If it's so novel, there's no one who has the vocabulary to understand it. I think of it in the context of like there's a beautiful notion in biology of hybrid vigor. Do people know what this is? So this really defined modern agriculture, this discovery that, you know, different strains of wheat, when crossed, end up producing much more agronomically robust wheat, in the same way that two different breeds of dog, if crossed, are much less likely to have, you know, chronic disease, are much more robust, or more likely to be intelligent, or relatively intelligent. And the reason is because each of those things have a different, you know, kind of selection, right? So that selection, there's different environments, there's different breeds, there's different species, end up, you know, kind of making them genetically interesting or relevant to each other, right? And so hybrid vigor is like two things that are relevant to each other. They have information, genetic information that's relevant or surprising to the other. When they mate, then the offspring do better on average. It's not fully understood biologically, but it's interesting. And the problem is, if you can't mate anymore, right? If they evolve so differently that they can't actually genetically communicate anymore, then there's no communication, right? Then there's no way for this species to communicate with that species. There's no way for their offspring to, and I think the same is true in these scientific systems. If you're so far away from the pack, you develop novel formalisms and novel concepts, then the population that's there cannot understand. You can't communicate that information with so I think, you know, when we see people who are really engaged in really radical difference, it's, you know, it doesn't travel. And if it travels, it's rediscovered, as Van Gogh was in the future.
Thank you very much for such a beautiful talk. I just have a question regarding the disruption hybrid graph that you mentioned, right? So there were like different catalogs and all those things, and then there were sometimes that it doesn't merge together. So like, in your opinion, like, is there any measures that we should put into the society that could be allowed them to like be more disruptive or something like that? Yeah,
that's a great question. I mean, I think it's interesting is that there's this thing about measures, you know, this problem with measures. It's a problem that's rediscovered by like every social science field that's looked at measures. They all have their own name for it. You know, sociology is Campbell's law, and in political science, it's Goodhart's law, and economics, it's the Lucas critique. And this idea is that if you have a measure that's correlated with a quality that you desire, you know, that you'll reward, then the system will drive the correlation between that metric and the quality to zero, right? Because it's easier to get the measure than to get the quality. It's easier to get citations than it is to get high quality papers, right? There's even, I mean, this is maybe seems like the extreme end. I love this example of there's a market, you know, for paper. You know, if I wanted to get promoted, I can pay for a company to produce a paper for me, produce data for me. There's one website that a friend of mine found in Eastern Europe that you could pay the website to hack into the editorial management system of a journal and insert you as an author in someone else's paper. I love that market. I mean, that's an enterprising market. I mean, that's really, you know, using some special skills. So at that point, you know, the number of papers on which you're an author has now, its correlation to the output is probably negatively associated with quality, right? So I think one of the challenges is, first, it's true that up until recently, folks at NIH and National Science Foundation of China, these organizations didn't have metrics for novelty, and they're hungry to get those metrics. But I caution them to use one, and I invite them to use several, so that we don't have this problem where you drive down. The citations is one of those things, where if you reward everything by citations, then there's going to be all kinds of activity in the scientific system that maximizes citations and drives down its quality. You get more citations if you publish a thing with barely any advance, but it's very close to things that exist in the system, right? It's encountered by accident, and referenced by accident, right? So I think one of the challenges is to build measures that capture different aspects of innovation. I've featured a few of them here: novel combinations of things, the likelihood that people perceive something to be a new thing, the way in which people talk about those things in the literature, using all of these measures together to capture the relative likelihood so that they're not hacked, basically. It's like teaching to the test. So yeah, I think there's an important there's an important market for new metrics and multiple metrics to capture these valued qualities.
Professor Evans, maybe we can take one question from the audience, and then we could say goodbye to the audience that's online. And just a reminder, at 8 o'clock, which is now, we have the Chicago Booth Economic Outlook, which starts online as well. So we'll wrap up with the online audience. But I thought this was an interesting question. It could have come from one of our students at UChicago or from one of our alums. They're wondering if there's any evidence that strange major combinations, like majoring in nuclear engineering and Greek lit, have any kind of impact on productivity on the job, because it's a diverse combination versus studying math and statistics, for example.
I think that's a great idea. And I think, I will say that in general, especially graduate education and less undergraduate education, education is a control system. So we've studied, a data set of about 10 million syllabi to figure out, what it is that people ask their students to study and who those people are who are writing those syllabi that are influential and driving other syllabi. And it's older people within disciplines that are influencing younger people in the disciplines. And so I think I love this idea that, we rethink education for innovation as every student is an experiment, right? Every student is an experiment combining new kinds of majors, new kinds of classes, new kinds of expertise, new kinds or novel kinds of projects. Now, this is going to make the labor market a little more complicated because, what is it going to mean for some student to advertise themselves as having a unique combination of skills that no one has seen before? And yet, this provides us with the opportunity, right, to start searching for things that we might not have been able to search for ourselves, and for basically testing a whole host of hypotheses. To what degree are issues, in Greek philology relevant, to the patterns of the way of thinking, in physics or biology or sociology or art history or whatever. So I think I would love to do that study. I don't know what the answer is. I think that it's likely that those students who have those combinations are likely to identify and follow diverse pathways in the future. But we don't know if that's just because those were the students who picked those things rather than that those are the things that caused them to have those outcomes. So that would require all kinds of fancy measurement. But I'd love to do that study. So email me and let's figure out how to do it.
How can we email you?
Evans, Jevans at uchicago.edu.
Great. Thank you so much, Professor Evans.
Thank
you. It was a great talk. I'm going to wrap up with the online audience, and I'm going to do so by saying, wouldn't you like to know how Professor Evans became a professor? I'm kind of curious. So we're going to invite him to join our new podcast, relatively new this year, called The Course, which interviews, we have about almost 70 interviews of our UChicago professors, asking them how they became professors, and then talk a little bit about their research. And we're going to invite Professor Evans to join the course so we can learn more about his background, which leads and led to this fascinating area of study. So you can find the course on Apple and Spotify and Himalaya. You can find it all kinds of places, but we wanted to just remind you that the course is out there to learn more about our UChicago faculty, professors, and their background. So thank you so much for everybody that joined us online tonight. Hope you joined the booth Economic Outlook. For those of you that are in person, I think Professor Evans will be around for a few more minutes to answer any questions that you may have. This is the beginning of something new and great, and we're looking forward to having you all back on campus again and virtually if you can't make it to campus. Thanks so much and have a great evening, everyone.